Welcome back, learner, to another deep dive. Imagine you're tasked with reading an entire library of technical manuals.
Oh, wow. Sounds exhausting.
Right, but there's a massive catch. To actually understand the final sentence of the final manual, you have to hold like every single word you've read previously in your active short-term memory.
Oh, yeah. Every single word.
Exactly. You can't just recall the general concepts. You need the exact phrasing, the punctuation of every line from every page, all simultaneously. I mean, human biology would just crash.
Yeah, we'd blue screen instantly.
We really would. We rely on compression. We summarize, we abstract things, and we let go of the raw data to retain the actual meaning.
Yeah.
But until very recently, that kind of brute force perfect retention is exactly what we've been demanding from artificial intelligence.
And that demand has created what we now call the memory wall. It's really the defining bottleneck of AI scaling today.
Memory wall. Let's unpack that.
So as we push models to process these massive inputs, swallowing entire software code bases or, hour-long video transcripts, their memory footprint just balloons.
Yeah.
The physical VRAM on the GPUs running them simply maxes out.
Which is why our mission today, for you, the learner, is so critical. We are exploring the foundational state-of-the-art research that's driving the next generation of generative AI.
Yeah, this is cutting-edge stuff.
It really is. Specifically, we're looking at the Kwai Summary Attention Technical Report. This was released by the OneRec team at Kwai in 2026.
Right.
And we're going to figure out exactly how their new mechanism, which they call Kwai Summary Attention, or KSA, allows an AI to read incredibly long sequences without its memory or, the actual server farm just crashing.
Yeah. And to really appreciate the elegance of KSA, we first kind of have to examine the nuts and bolts of the current bottleneck.
The why behind the what.
Exactly. Like why large language models struggle so profoundly with long contexts. It all comes down to the architecture of what we call vanilla attention. There are basically two distinct scaling problems happening under the hood. The first is the attention computation itself, which scales quadratically.
Right. So if you double the amount of text you feed into the model, the mathematical operations required to figure out the relationships between words don't just double, they quadruple.
Precisely that. Because every new token has to calculate its relationship to every single previous token.
Which is a lot of math.
It is. But the second issue, and the one that actually breaks deployments in the real world, is the KV cache.
The key value cache.
Right. During autoregressive generation, that's when the AI is, spitting out an answer token by token. It stores a mathematical representation of every previous word in this cache.
So it doesn't have to recalculate the entire document from scratch for every new syllable.
Exactly. But the fatal flaw here is that this cache scales linearly at a strict 1-to-1 ratio.
A 1-to-1 ratio.
You feed the model 1 million tokens, it requires 1 million dedicated slots in its VRAM cache, period.
Wow. So the industry has obviously been trying to engineer around this, right? From what I understand, reading the sources, researchers have generally split into two distinct camps to try and solve this.
Yeah, two very different philosophies.
The first approach is trying to, shrink the size of the tokens themselves. Methods like group query attention GQA or multi-head latent attention MLA.
Right. They compress the dimension or the heads of the attention mechanism.
Which essentially shrinks the memory footprint of each individual word.
They do. And, it buys us some headroom. It helps.
But if we think about it like taking notes on that massive library of manuals I mentioned earlier, that approach is basically just switching to a much smaller pen.
I love that analogy.
You're just writing in a microscopic font to save paper. It delays the inevitable, sure, but because of that strict 1-to-1 ratio you mentioned, you are eventually going to fill up the notebook.
Every new word still demands a new note.
Right. So what's the second camp?
Well, that realization naturally led the industry to interleaving KV-friendly architectures. This includes methods like sliding window attention SWA and gated deltanet.
Okay, and how do those work?
They abandon the 1-to-1 rule entirely. Instead of keeping everything, they selectively throw data away.
Wait, really?
Yeah. Sliding window attention literally just slides a fixed window of memory over the text. It only keeps the most recent tokens active.
That seems like giving the AI a severe case of amnesia.
It essentially is.
Like if I'm asking an agentic coding model to find a deep-rooted bug across a massive repository, a sliding window means it completely forgets the first dozen files it read by the time it reaches the end.
Exactly. The distant past is just gone.
So are we just stuck choosing between running out of physical hardware memory with the tiny pen approach, Or giving the AI goldfish memory with the sliding window.
Well, the Kwai report argues that the space between those two extremes has been severely underexplored.
Okay.
Their solution, KSA, introduces this intermediate path they call semantic-level compression.
Semantic-level compression.
Yeah.
How does that avoid the one-to-one trap?
Instead of a one-to-one ratio, KSA divides the memory burden by a fraction. It partitions the input text into distinct chunks.
Chunks of words.
Right. By default, the report says they use a chunk size of 8 tokens. So the model reads 8 tokens, and at the boundary of that chunk, it injects a brand new learnable summary token.
Oh, wow. So it's actively synthesizing as it reads.
Exactly. And it does this through a really elegant, highly constrained dual role system that governs the flow of information.
How so? What are the constraints?
Well, the summary tokens are heavily restricted. They are only allowed to look at the text within their specific local chunk.
So just those 8 words.
Right. Their singular job is to distill the local semantic meaning of those 8 words. Meanwhile, the text tokens, the actual words of the document, operate under a completely different visibility rule.
Okay, what can they see?
A text token can look at its immediate neighboring text, but to understand the distant past, it is only allowed to look at the summary tokens from previous chunks.
Oh, I see. Let me try to ground this for you, the listener. It's like binge reading an epic fantasy series.
Okay, I'm with you.
When you're reading the newest book, you're reading the current chapter word for word. You're deeply in the weeds of the dialogue and the action. But to remember what happened, like 3 books ago, you don't reread the entire old book.
No, of course not.
You just reference a Wikipedia plot summary. You just need to know that, the king was betrayed in chapter 4 to understand why the current battle matters. You rely on the summary token.
That captures the dynamic perfectly, actually, and the trade-off is profound here.
How so?
You're giving up a tiny bit of local granularity in the distant past, but in exchange, you get complete interpretable retention of long-distant dependencies.
Because you aren't throwing the past away entirely.
Right. In a standard linear model, as the context grows, the past gets mathematically blurry. The attention weight gets diffused across tens of thousands of tokens.
Everything just blends together.
Exactly. But with KSA, that summary token acts as a concrete, highly concentrated referential anchor to the past.
So mechanically, how do we move through the document? Because earlier we talked about that sliding window idea.
Yeah, SWA.
Right. If I take a standard sliding window and just drag it over these new KSA chunks, problem solved, right? We just slide along, reading the chunks and summaries.
You'd think so, but doing that actually breaks the model entirely.
Wait, really? Why does it break?
This is a vulnerability the researchers really had to solve. Think about the physical boundaries. A standard sliding window attention slides forward arbitrarily, token by token.
Okay.
So if it slides over an 8-token chunk and stops halfway through, the window just cuts the chunk in half.
Oh, I see. So the model only sees 4 text tokens.
Right. And worse, because the chunk haven't finished, the summary token hasn't been generated yet.
Oh, no.
Yeah. The model becomes completely blind to half the local information, and it gets no summary of what it missed. It causes massive information loss right at the seams.
So it creates artificial blind spots just based on where the window happens to randomly stop.
Precisely. To fix this, KSA introduces sliding chunk attention, or SCA.
Sliding chunk attention.
Yeah. The window boundary is forced to align perfectly with the chunk boundaries.
Okay, so it's a hard stop.
Exactly. The model either sees an entire chunk of text or it doesn't see the text at all and relies exclusively on the summary token for that block. There is no halfway.
That is a very clean constraint.
It is, but the brilliance of SCA isn't just algorithmic. It's about hardware harmony.
What do you mean by hardware harmony?
Well, during autoregressive decoding, your GPU is rarely compute-bound. The math isn't actually the slow part.
Wait, it's not.
No, it's memory-bound. The bottleneck is the physical time it takes the GPU to fetch fragmented data from across the VRAM.
Oh, because it's trying to gather scattered bits of memory from, like, 100 different locations on the chip.
Exactly. It's super inefficient. KSA solves this by organizing the KV cache into physically contiguous tensors.
Meaning they sit right next to each other on the hardware.
Yes. They divide the memory into 3 distinct blocks: the current chunk, the sliding chunk text, and the summary token buffer.
And because of those rigid boundaries of sliding chunk attention you just mentioned.
Right, because of those boundaries, these blocks sit adjacent to each other physically, The GPU can sweep through and read the required memory in one massive, clean fetch, rather than piecing disjointed memory blocks together.
That is incredibly smart. Okay, so KSA shrinks the token count and it optimizes the VRAM fetching.
Yes.
But let's go back to those other methods we discussed earlier, GQA and MLA.
The tiny pen approach.
Right, the tiny pen methods. Are these competing philosophies? Like, if an engineering team adopts KSA, do they have to throw out their existing GQA optimizations?
This is where the math gets truly spectacular. They don't compete at all.
Really?
Not at all. KSA is fully orthogonal to GQA and MLA. They operate on entirely different mathematical axes, meaning you can stack them.
How does that actually work in the formula?
So, the total size of your KV cache is calculated by multiplying three variables: the number of tokens, the number of attention heads, and the embedding dimension.
Okay, three variable.
Right. KSA attacks the first variable, reducing the number of tokens by replacing them with summaries. GQA attacks the second, reducing the number of heads.
And MLA attacks the third, reducing the embedding dimension.
Exactly. Because they each target a completely different variable, you can multiply their compression rates together.
Oh, wow. That compounding effect must be massive.
It's unbelievable. The report lays out the specific numbers. When you combine KSA with MLA, the total KV cache size drops to 0.22% of a naive full attention model.
0.22%.
Yep.
I mean, that is not a marginal efficiency gain.
Yeah.
Let me pull up figure 10 from their technical report just to give you, the learner, a sense of scale here.
That's a great chart.
They stress tested this at a 128,000 token context length. To hold that memory, a standard full attention model consumes 18.6 gigabytes of cache.
Which is huge.
It is. But the KSA model, combined with these other methods, uses only 7.5 gigabytes.
Right.
And because it's bypassing that memory bandwidth bottleneck we just talked about, it actually has a higher decode speed. It generates answers faster while using a fraction of the memory footprint.
It fundamentally reshapes the resource requirements for long context generation.
It really does.
Yeah.
But, and I have to ask, this hardware efficiency means nothing if the model hallucinates or loses comprehension, right?
Oh, absolutely.
So does this heavily compressed, heavily summarized model actually retain the intelligence?
The evaluation phases were incredibly rigorous to ensure exactly that. The researchers didn't just bolt this onto an existing model and call it a day.
What did they do?
They tested a train-from-scratch model, exposing it to 400 billion tokens, and a continual pre-training, or CPT model, trained on 85 billion tokens.
Okay.
And crucially, they engineered the data mixture so that 55% of the training data was specifically focused on long context tasks.
Basically, to force the model to rely on its summaries during training.
Exactly. They made it practice the hard stuff.
So what happens when we put it up against the ruler benchmark? Because that's the standard stress test for long contexts, right?
Yes, it is. And the results at the extreme 128K link are fascinating. The standard full attention model, the one that retains a perfect verbatim record of every single word degraded rapidly as the context stretched.
Right.
It scored a 48.75. But the hybrid KSA model scored a 65.35.
Wait, I need to pause here.
Yeah.
Why does the model that keeps a perfect record of everything score significantly worse than the model that is actively throwing away text and relying on summaries? That feels completely counterintuitive.
It really does at first glance, but it comes down to the signal-to-noise ratio.
Signal-to-noise ratio.
Right. When an attention mechanism tries to hold 128,000 exact tokens simultaneously, the attention weights become incredibly diffuse. Every single word is shouting for attention.
So the model basically gets lost in the noise and loses track of what actually matters.
Exactly. The summary tokens in KSA, on the other hand, act as highly concentrated signals.
They filter out the noise.
Yeah, they filter out the noise of the exact phrasing and present a clear map of the semantic meaning. This prevents the model from hallucinating or losing the plot.
Okay, that makes a lot of sense. But what about pinpoint retrieval?
Like finding a specific fact?
Yeah, like if I hide a specific serial number or a single crucial sentence deep inside a 100-page document, does the summary token just abstract it away, or can the model still find it?
They ran the needle in a haystack benchmark to test exactly that scenario.
Yeah.
The model achieves near-perfect retrieval of specific facts buried at any depth within the 128K context.
Wow, even with the compression.
Yep. And it does this while maintaining top-tier performance on general knowledge benchmarks like MMLU, math reasoning on GSM-8K, and coding on MBPP.
That's incredible. Now, you mentioned hybrid KSA just a moment ago when we were discussing the ruler scores.
Yeah.
What makes it a hybrid architecture?
Well, the researchers found that applying KSA to every single layer of the neural network actually wasn't optimal.
Oh, really?
Yeah. Instead, they use a 3-to-1 mixture ratio.
Okay, what does that look like?
They stack 3 summary attention layers, followed by 1 full attention layer, and they just repeat that pattern.
So 3 layers of summarization and then 1 layer that is permitted to look at the entire uncompressed context.
Exactly.
Why that specific ratio? Why not all summaries?
When they visualized the attention weights during inference, they discovered this really unique synergy. The KSA layers form a periodic comb-like attention pattern.
Comb-like?
Yeah. They scan the summary tokens, acting kind of like a rhythm, highlighting the general areas of importance across the whole document.
Hey.
Then, that rare 1 in 4 full attention layer acts as a cross-chunk integrator. It takes the general map provided by the summaries and spikes its attention directly on the crucial local details.
It is essentially teamwork then.
Exactly.
Like the summary layers are acting like scouts. They run ahead, they survey the landscape, and they point to the general quadrant where the enemy is hiding.
I like that.
And then the full attention layer is the sniper. It doesn't have to waste time scanning the whole forest. It just looks exactly where the scouts pointed and zooms in on the target.
That is a very apt analogy. The summaries provide the global routing, and the full layer provides the local precision.
But introducing this architecture brings up a massive practical hurdle, doesn't it?
What are you thinking?
Well, if we are injecting summary tokens, creating these dual role visibility constraints, and building this custom 3-to-1 layer ratio, doesn't that bloat the parameter count?
I see what you mean.
If I'm a developer trying to deploy this model, am I having to download a significantly heavier model?
You would be if it weren't for the elegance of their 3-stage continual pre-training recipe.
Oh, so they solved this in training.
Yes, they completely engineered away the deployment bloat. Stage 1 introduces independent, learnable parameters specifically for the summary tokens.
Okay.
And to train them quickly, they use multi-granularity distillation.
Distillation. Okay, so they take a massive, fully trained teacher model that already knows how to do full attention perfectly, and they use it to tutor the new KSA student model.
Yes, exactly. They force the student model to match the teacher's outputs at multiple levels.
Like what?
Well, matching the hidden states layer-wise, matching the attention distributions, and matching the final objective logits. They basically rapidly teach the new summary tokens how to effectively capture the same semantic weight as the raw text.
That makes sense.
But the true magic happens in stage 2, which they call parameter annealing.
Parameter annealing. Walk me through the mechanism of that, because it sounds like where the real efficiency is unlocked.
It is. During annealing, the training process gradually weakens the boundary between those special summary weights and the standard model weights.
Okay.
Mathematically, it linearly interpolates the two. Over thousands of training steps, the model blends the knowledge it learned for the summary tokens directly back into the main parameters of the underlying language model.
So it absorbs them.
Yes. If we use an analogy here, it is like teaching someone to ride a bike with training wheels.
Okay, training wheels.
The separate summary weights are the training wheels, right? They provide a distinct, separate mechanism to keep the model balanced while it learns the complex task of summarizing chunks.
Right.
But parameter annealing is the process of gradually raising those wheels off the ground until the writer's core muscles, the main parameters of the LLM, have completely absorbed the balancing behavior.
Oh, wow.
And by the end of the training run, you just take the wheels off entirely.
I love that. So when you and I download the model for inference, the training wheels are totally gone.
Gone.
There are 0 extra parameters. The model has just internalized the behavior of semantic compression without requiring any permanent extra hardware to execute it.
It is a profound optimization. The model becomes intrinsically capable of summarized attention without any structural bloat.
So what is the ultimate takeaway for you, the learner, in all of this?
Yeah, let's bring it back to the big picture.
Kwai Summary Attention is clearly not just a clever mathematical trick to save a few gigabytes of VRAM on a server. It's a foundational bridge to making true agentic AI a reality.
Absolutely.
We are moving toward a future where AI needs to hold context across days, weeks, or even months. You know, an agent that can read an entire proprietary code base reason about the architecture, write new functions, and debug its own work without suddenly forgetting the core logic of the very first file it read.
And crucially, KSA allows us to run these massive context horizons without requiring a trillion-dollar supercomputing cluster for every single query.
Right.
Because efficiency has really become the true frontier of AI scaling today.
It has.
We have thoroughly proven the scaling laws, right? Feeding models more data and giving them more parameters makes them inherently smarter. But we are slamming into the physical limits of power consumption, memory bandwidth, and silicon.
There's only so much juice we can pull from the grid.
Exactly. The Kwai technical report proves that brute force scaling isn't the only way forward. We don't just need larger models. We need infinitely smarter architectures. We need models capable of organizing, compressing, and structuring their own cognition.
Which leads me to a final thought I want to leave you with today.
Ooh, all right.
If an artificial intelligence is actively learning to rely on highly compressed semantic summaries of its distant past, rather than maintaining a perfect verbatim recall of every single token,
Yeah.
isn't it beginning to mimic the very nature of human memory?
Oh, that's an interesting point.
Right. I mean, we don't remember every single word of a conversation we had a year ago. We remember the summary. We remember the feeling. We remember the core concept.
They compress it.
Exactly. We have always viewed the AI's perfect digital recall as a feature and human forgetfulness as a bug. But could this lossy memory, this forced abstraction, actually be the necessary prerequisite for higher-level reasoning?
That is a deep thought.
Perhaps perfection is the enemy of understanding, something to mull over. Thank you for joining us on this deep dive. Keep exploring, and we'll catch you next time.